Greetings, student. This is a recording of one of Garnett's online math lesson classes. You have been granted access to watch this video because you're a paying student and I have seen it fit to provide this recording to you. However, it is important that you know you're not allowed to share this video with persons outside the lessons. This policy is so that my services are kept only to my students. Thank you, and I do hope you enjoy and learn from this video.
So continuing from where we left off, we were about to, I was about to go and interpret some data for you using World Wide Web, right? The internet, Google, for example. All right, so what you notice here, and this is something, so what we're looking at is the rise in new cases of COVID in Guyana for the past 2 weeks. 2 weeks is the number to work with, right? For the past 2 weeks. So from December 29th to January 11th, right? Now you notice as I go through each of them, there's a point, right? This is a line graph, and look, you can see their scale 0, 500, 1,000. So their scale is every 500, but I'm not sure what the unit of measurement is here. Unimportant. Computer did it, but what you'll notice here is that there's this superimposed what you notice here is that it superimpose a bar graph and a line graph on each other. That is something you can do. Now the usefulness of that, we'll get into in a second. So looking at this line graph, you'll notice, one thing you notice right away is that the line this should be pretty obvious, but one thing you'll notice is that usually once you're reading your data, you usually read your data going across in this direction, right? In ascending order, usually this is ascending order, but you usually read your data set going in this direction. Graphs in particular, you usually read it going in this direction. Line graphs, maybe a bit more specific. When you're reading line graphs, you usually read it going in this direction. And you try to identify your trends, again, going in this direction. So as we go from December 30th, we can read. So as we go from December 30th to January, then to January 3rd, 5th, 7th, they're skipping days, right? It's here, but they're just not labeled. 9th and then to 11th, you notice that the line just keeps going upwards, right? The line just keeps going upwards. And now what it tells us is that the frequency increases with increase in time. So as you go up, whoa, what just happened? Good. So what we notice as we go in this direction, right? As you go from 30th of December all the way to January 11th, we notice that COVID cases are just going up, right? The line just keeps going up, right? And right away that tells us that our observation, as we increase our observation, the number of COVID cases or the frequency increases, right? So the relationship that we can gather here because of the data set we're looking at is that as more and more days go by, more cases seem to be arising. And you already know this, it's been in news, the news, but you can look at graphs and identify this. Now, something else that you got to be able to read off once you're looking at baseline graphs is, I will make a note of these things, just not to worry. Good. So you see here, You see overall the entire world, cold cases just seems to be climbing from since December. It's probably because it was a holiday, more likely because it was the holidays and everybody went outside and good. So you notice here, again, these are straight lines, but as you zoom out, it, it's gonna look like curves, but these are all straight lines connecting all these points. But so what you notice here is that the line goes up. Again, we usually read again in this direction, right? You won't find someone reading it back like this, backwards. That would be good. So, so you so you generally read going in this direction, and you notice that it goes up, and then once it reaches November 25th, it comes down and then goes up and then goes down and then go up. Now this is something that you see happen with data sometimes. You got to be able to interpret it. So what's happening here, some terminologies that we use is that in let's say between November and July, the number of COVID cases fluctuated between November and June, right? Not July, June. So your data can fluctuate. Your data can go in an upward trend relative to your frequency. Observation can go increasingly with your frequency. It can even go in the downward trend. It could decrease over time, that kind of thing. Those are the kind of information you'll be looking for with a line graph. Now, I think you guys get that. So let's go back to our data set. Good. So this is a perfect example of fluctuating number of cases, right? This is a perfect example of our data set fluctuating. So you notice it comes down, then it goes up. That's the reason why you join the points with lines, is so that you can see that, well, okay, it's coming down, the line comes down, then it goes up, down, up, down, up, down, 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 right? Then it inevitably starts going down, right? And this is generally the information the statisticians use to make, and even politicians. Statistics is one of the most, like I said before, statistics is one of the most important parts of maths, and it's a really important part of our lives in general, because a lot of decisions are made based on statistics. That is a controversial topic, something controversial to talk about, but I'm not going to get into that. But you can see, at least you should be able to see that knowing how the observation responds in relation to frequency over time, right? Knowing how the COVID cases especially is fluctuating, if it's increasing, if it seems to be inevitably increasing, you know, you got to make changes and so on. So from statistics, from these graphs, from the data, is what we use to actually make decisions, and we interpret. So from interpretation of the data set, you go towards your discussion or decision making, right? You use it to decide, okay, what's going on. You try to explain why that's happening. Why is the cases going up and then down and then up and then down? Why is it going all the way? Why is it going up all the time? Why is it going down? You try to explain, try to look for reasons for that. Now the explanation you might not have the explanation yourself, all right? You might have to go and look, right? You might have to go and do a survey to see why. You might have to go and, right? So generally, that's what the line graph is used for. It's used to identify upwards and downward trends. The only difference, there's only one difference between this and the line graph. See that just now, right? So a frequency polygon is a statistical diagram that indicates the spread of a given distribution. Let's see what that means just now. Good. So a polygon originates from plotting consecutive points should remember your line graph. They are obtained by plotting the observation versus the corresponding frequency. We did that with the line graph. Then drawing straight lines to connect them together. We did that with the line graph and the horizontal axis. We didn't do that part, right? We just connected the lines together. So your frequency polygon is your line graph, but an additional step. So that's what I want you to think of your frequency polygon as. So think of your frequency polygon, everything like your line graph, but there is an additional step with your frequency polygon that you do, that you want with your line graph, right? The same thing with the axis. The frequency is on the vertical axis. And again, I've been drawing this. The vertical axis is this one. By now, you should know this the heart, right? You should know this by heart. The observation or control variable is on your horizontal axis. That is the axis going this way. And temperature data is the same thing. But one key important thing about your frequency polygon. If you think about the frequency polygon, yes, you can identify upwards and downward trends within the data set. You can't do that because, again, it's sort of like a line graph. But one important thing about the frequency polygon, it also does is that you actually can find your total frequency by looking at the area of the polygon that is formed, right? So the area of the polygon that is formed is actually directly proportional to your total frequency. And you'll see an example of that just now. And I'll show you guys how to calculate it. But for the group data set, when you have group data, even with your line graph, we use the midpoint, the class midpoint, right? We went through what class midpoint is before. You use the class midpoint and plot that, use that as your observation and plot that against your frequency, right? You don't need to use it as a group. Okay, you'll see an example of that just now. So we have a frequency polygon on group data. We will look at one group data, right? Again, think of, I don't want you guys to look at the frequency polygon as an entirely new graph. It's not. It's just your line graph, but with an additional step, right? So I'm going to go straight ahead and start plotting the frequency polygon. So on yeah. Yeah, so on my right, you will see this data set, question number and number of students who answer correctly. Again, this first data is our observation column. The first column in our table is our observation column, and the second column is our frequency. I'm saying that all the time so that you guys can identify what is your frequency and what is your observation, even if it's not labeled frequency and observation, right? Usually this is how you put it. Now, when you're doing your tables, please put your observation column first and then your frequency, right? Good. So the first step again is usually to draw your two axes. Next is to come up with a suitable scale. Like again, it's your line graph, but with that additional step. So we have to come up with a suitable scale that includes all of our observations because we're reporting the x-axis, right, or the horizontal axis first. So it's from 1 to 16. We could just use every small box is equal to 1, but that would make it a bit too small. So we're going to do the same thing like before when we were plotting against time versus COVID cases. Every 2 box will be a number, question number, right? So add in your graduations. Yeah, add in your graduations for your horizontal axis and then start labeling them, right? Again, every 2 box, right? The scale I will use is every 2 box. You could use every 3. Again, it depends on how much you want. You could even use 2.5, right? You could use 2 box and a half. I don't know why you'd put yourself through that struggle, but you can, right? You can use whatever graduation you want to use. Just ensure that, of course, It's the same, right? The distance is the same between each graduation. So for every 2 boxes will be a graduation. Again, small boxes, right? 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, on and on. You get a point. Next is to plot to label them, right? It's question number 1 all the way to 16. And we know we're going in ascending order from left to right. That's how we plot our graphs, right? At least the positive values. Ascending order from left to right, all right? 2, 3, 4, 5, 6, 7, 8, all the way to 16. So this is a suitable scale. It fits all our observations and done and dusted there. Next is to go ahead and plot our vertical axis, graduation. And again, what you want to do is identify the highest frequency. That is 12. I said 11. The highest frequency is 12 and the lowest frequency is 7. So when you pick your scale, it needs to include 7 and 12. So we could just count numbers like this. Yeah, this is the same simple, right? So let's go ahead and plot our frequency, which is number of students who answered the question correctly. So 1, 2, 3, 4. Right, and again, the same scale here. Every 2 boxes is a graduation. You will pick your graduation, just ensure that it includes your lowest and highest frequency. You'll be fine, right? There's no need to approximate. We're using every 2 boxes is 1, right? Or every 0.4 centimeters is 1, right? So we just go ahead and label. We go from 1 to 14. We don't need to stop at 12, but could go all the way up to 14. So this is our scale, right? Again, the x-axis is your horizontal axis. So let me label it again for you if you've forgotten. This is what we call the x-axis, and this is what we call the y-axis, right? I'm referring to them as horizontal and vertical because we haven't looked at variables, these line graphs as yet, linear functions and graphs as yet, right? So the x-axis, which is our horizontal axis, every 2 boxes, which, like I said, you need to use a unit of measurement and not 2 boxes. And we know every box is 0.2 centimeters. So every 4 centimeters represents 1 question number. So 1, 2, 3, 4, every 2. Now on the y-axis, we use the same thing, or on the vertical axis, we use the same scale. Every 2 boxes is 1 student, right? You got to be able to correlate the data that you have with what number these represent, right? These numbers actually represent number of students, right? And these numbers here represent question number. You got to remember this. These numbers are not just there for decoration. They actually mean something, right? Question number here. The rules for your scale is it must fit all your data. So all your data must fit within that scale. It must be somewhere there. And the graph must take up approximately, this sign means approximately, right? I use this sign here because in case you didn't know this before. Right, this sign, this squiggly sign means approximately. And this means approximately equal to, right? Is approximately what would equal? I will have to erase all of this. Good, so the graph must take up 80% of your graph paper. So if you pick too small of a scale, then what might end up happening is that you might end up plotting your points like right here, and your graph is like this small, and you have all of this space that you're not doing anything with, right? So that's why this second rule is there, and you lose marks to that, right? You lose marks to that. Unfortunately, you will lose marks to that. So you need to take up at least 80% of your graph paper. So when you're picking your scale, it must, two things to consider is that it must take up 80% of your graph paper, and it must of course include all of your data, right? When you start plotting the graduation and it doesn't include a number, let's say I went all the way to 24, right? 24, and this would have stopped at 17, 18, 20, then I would have need to pick another scale, right? So all the numbers must fit on that, must fit. Yeah, all the numbers must fit on your axis. So you got to pick a scale that fits all your data. Same with the frequency. So now the now this doesn't always work, which is why I'm not too keen at showing it out there. But what you usually do is you just take your highest, you just take the highest value and divide that by divide that by 5. Usually divide by 5 because it's 5 boxes, right? So that's where the 5 comes from. Because it's 5 boxes, you want to divide this for every 5 box, the highest value by every 5 box. Usually you do this so that you know what the graduation is. So for example, let's look at our highest value. Right, our highest value is about 5, 26, 8, 9, 3. Right? You take your highest value and you divide it by 5, right? Again, it's sort of 5 boxes, so every 5 boxes, right? That's why you divide it by 5. It means that you're using a scale for every 5 boxes. Now, this should give you, what does this give you? 5 divided by 5. 526,893 divided by 5. What does that give us? That will give us some fancy decimal, I know that. Somebody go in and find it for me. All right, so we got about 105 or something like that. 100,000. 5, 3, 7, 8. I'll just write it off here. So we got this. Right? Good. And what you go ahead and do with this value now, and you would use this value for every 5 boxes, you would use this value, right? So that's what you would typically do. Sometimes it works. It doesn't always work. Sometimes it works, right? So instead of using every 5 boxes equal to 100,000, I can use every 5 boxes equal to this, right? But it's hard, right? If I use, so instead of this, I would use 105. So it's 79. And to figure out what the next value is, you need to add, of course, is every 5 boxes is this value. So you need to add this value to this value, and you'll get here, and then add it, and add it, and add it, and add. You end up with some fancy numbers. I can tell you that right away. So that trick doesn't always work, and I know it's something that if your teacher didn't teach you that, your teacher probably gonna show you, right? It doesn't always work though, but there are cases where it does. So so I am putting it here, putting it down here for you. So take your highest value and divide it by 5. That you can use that to come up with a scale, right? But if you start plotting the values and it doesn't fit, again, remember your rules, and it doesn't fit on the graph paper, the graduation doesn't fit, then you need to start decreasing, right? So you can decrease it instead of every 5 boxes being the highest value divided by, instead of divided by 5 boxes, if you want to say every 2 boxes, you can take the highest value and divide it by 2, right? Or you can just freehand. You can freehand and say, okay, I'm going from 1 to 16. I will just use every 2 boxes as 1. And that is what I did here. I'll just use every two boxes as one because it seems to fit. It seems to fit here, right? I didn't divide anything by anything, just decided to use this, right? That's something you could do as well. Of course, that'll come with practice, right? So you just need to ensure that this and this and these two rules are satisfied and your scale will be fine. That's it concerning the scale. Spent enough time on it. Right? Again, our scale is the same. 0.4 for every one. 0.4 for every one. So every one. Now let's go ahead and plot the points. I've already went through how to plot the points with you. Again, just go to your observation. Observation is 1. And we're going to go up. For 1, the frequency is 11. So observation 1, the frequency is 11. So for question number 1, frequency goes up all the way to 11. So we plot our point here. Frequency for observation 2, the frequency again is 11. So we go from 2, we go all the way up to 11, right? Notice I'm coming at, or 3, it's 12. So we go from 3 all the way up. Following this line, right? I'm not staying on the line I should be. All the way up to 12. It's 12. I gone past 12. This is 12. You rinse and repeat that for all of your observations, and you will end up with your points, right? So that's what we're doing here. 13, you know the step. And then you just draw a line connecting each. Again, don't take a line, don't try to cheat the work and draw a straight line through here. Take your time, right? I kind of missed this one, but take your time and do it. So this is our line graph. Up to this point, it's a line graph, and this is what you would call a line graph. But if we want to turn this into a I'll have to erase this just now, right? If we want to turn this into a frequency polygon, what we would need to do is add in an extra observation, right? Now using this scale, every two boxes being 1, or every 0.4 centimeters being 1, you can already guess what the next number is going to be here. What would that be? I'm asking the class. What would the next number here be?
17.
17, right? So you put in that extra observation. So all of our observations stops at 16, but you actually put in that extra observation there. And you also, yeah, that's it. That's the extra step. And once you've done that, you guys probably didn't hear that. You add a point at the end. Yeah. Add a point here and a point at the beginning. So we have a point at the beginning now at 0. We had a point at the end here at 17. At 17. So this is our this is our data. These are additional step. We're adding 2 extra points to our data set. 0, and you can say boundary points. 0 and the next observation. And of course, for the next observation, the frequency is 0, right? Because we didn't observe at this frequency, at this observation, right? So 0 here, again, the point is going to be, there's no 14, 12, nothing, it's 0. So the point goes on 17 and the point goes on 0. So we add an additional observation using the scale. We add an additional observation and we have our 0. Now, like what we were doing all the time, connecting all the points, you need to connect these 2 points in as well. And you notice this gives you a nice polygon. This will give you a nice polygon, right? If you look at it like this will give you a nice polygon. This is a polygon. Can't remember what a polygon is. It's a shape, right? It's a shape, straight line shape with more than say more than 4 sides, right? If it has more than 4 sides, it's a polygon. Quadrilaterals is 3, triangles with 3, quadrilateral with 4, more than 4. We just kind of call it polygon. I know there's types of polygon, you have a hexagon, and so on. But this you won't you can go ahead and count all the sides here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. 18 sides, right? Not sure what an 18-sided polygon is called, but this is a polygon, right? This shape is what we would call a polygon. So this is why it's called a frequency polygon, because we created polygon within our data set by adding 2 boundary points, right? The 0 and that additional observation at the end where the frequency is 0. Good. So we have our polygon. What you would go ahead and do now is to calculate the area of the polygon. Now that sounds like a lot of maths, right? That's like some extra math, but you don't actually calculate this. You actually calculate it, but the way to calculate it is not. I gotta erase this. Polygon. Of course, every graph should have a title. So you have our frequency polygon. Yes. Now, how do you get the total area? So the area for the total frequency. So once you got the area of this polygon, should be equal to the total frequency. Now, of course, you will tell me I could just calculate total frequency by adding these numbers together. And I would tell you go ahead and do that and not this. What I'm about to show you. It's easier to go ahead and do that, right? Total this together. But if you ever actually have to calculate the area of the polygon, you need to know to be able to do that. But for frequency polygons, the area is actually equal to the total frequency. That's just a neat concept that you need to remember, right? But you also need to know how to get the area. So to get the area, you don't have to actually there's no formula. You actually go ahead and this is what you do. You count how many squares. Yes, you count how many squares are within this matrix, within our polygon matrix. You count how many squares are in here. So 1, 2, 3, 4, 5. I'm not gonna sit down here and count all those squares. Yeah, right. I have time, yeah. But you usually count every square in here. Now, okay. You gotta count how many squares are there. In the exam, you actually have to do that to find area of any polygon or figure on a graph. So if you ever have a shape on a graph paper, so when you end this and keep, because CSEC sometimes will bring a question like this. Let me show you guys. Let's use this because I actually want to do this and not just talk about it. So let's actually do an example and count squares and find the area, right? Of shape. So let's use this instead. Your graph paper, typically your graph paper actually have the 1 centimeter boxes, right? This graph paper that I'm using here only has that 0.5. That point, the small boxes. You would have a bigger box. You can count the bigger box. So what you got to do now? So let me show you. Once you actually found it. So let me just draw a random shape. This will work for the frequency polygon as well as this, right? As well as any polygon that's on a graph paper. This is how you find the area for it, right? So looking at this, instead of using the small boxes, I can actually use these larger boxes, right? And you will have a graph paper that will have both the small boxes and the larger ones, which is really good because you can use those. Now, so this is 1, so let's count and use the same strategy that I showed you. So this is 1, we'll count this as 1. It's just missing a piece. We still count it as 1. these areas are approximations. They're not actually the real area of the polygon. You don't get, none of you should actually get the same answer for these polygons. If you do, it means that you cheated. But you don't always end up with the same area. But once you're counting and you're approximating correctly, more or less you should end up in a certain range, right? That the examiner will mark you for. So for these kind of questions where you find the area of a polygon on a graph paper, and you got to count these boxes, you might count like how I was saying, Kezia, 34 is definitely wrong. She might count 34, I might count 36. She might count 161. No, that's a joke. I'm kidding. She ain't supposed to count that high, but all our values should be within a certain proximity of each other, right? And the marker understands that. So there is no same definite answer for these areas. It's just an approximation once you're counting these. Because you notice I'm saying you choose whether or not, okay, these two can count as one, you know, these two count as one, and what's not, right? So let's go ahead and count. So one, I'm counting this for this missing piece. This is like a small piece to add it on. So this is 1 centimeter. I could actually do this. So this is 1, and then this is 2. This is 2, and this is 3. Now you see 3 has a missing piece. We'll just add this piece up here to compensate for that top piece missing there. So that'll be 3. So let's just, you got to remember though, right? Just remember this piece is with this number 3 here. And then you have, okay, so this we got a piece of to help this guy out. I could use this piece over here. Could use this piece over here. So this is 4. Again, we're using this piece over here. And then we have this guy. Notice I'm going around the edges first, because the edges is usually the hardest one to count. The boxes in the middle are easy. So we got 4 so far. And you go ahead, you go again. So a piece missing out here. It's not a full box. A piece is out here missing. Let's use, this is too much. Yeah, let's use this piece at the bottom here, right? Count that as 5, right? So this is 4. Using the same number, these 2 are 4 and these 2 5. So I could actually label these 2 as 3, right? Good. So we're following so far. This is 6. Right. Okay, we need a piece to compensate there. Let's use this guy. This piece over here. Let's count that as 6. Piece 6. There's a bit of, okay, that's 6. All right. So a piece missing out here. Let's use this guy, this piece that is out here. So 7, and you'll be 7 as well. So we count 7 boxes for sure so far. Okay, this look like a complete box. There's 8, 9, 10. Okay, you need another piece to compensate. You ran out of pieces to compensate, unfortunately. I forgot who we add this piece to, but nevertheless, we'll count this as 11. Right, this will count as 11, even though it's missing a piece. This piece is, I want to say, this would be 12. You could do 12 and a half if you want. You could say a half if you want. Again, these are all approximations. Let's just do this as 12. And then this is a full box here. So 13, 14, 15, 16, 17, 18, 19, and 20. So we count 20 boxes, approximately 20 boxes. So I'll put the approximation in front here. Approximately 20, and these are 1 centimeter boxes, right? These boxes will be 1 centimeter. Don't look at the graphic right now. This is a bad example. It's not actually a 1 centimeter graphic, but use your imagination. So the graphic you're going to be looking at will be 1 centimeter boxes. These large boxes will be 1 centimeter boxes. The small ones we know is 0.2 centimeter boxes, right? Don't forget that. Don't forget that. Keep that in mind. Right? So what would be the area for a 1 centimeter box? For these 1 centimeter box, what would be the area? Any one of you? What is the area of one centimeter box? None of you can't tell me the area for this 1 centimeter box. The area for the box itself. What would be the area? All right, hint is it's a 1 centimeter box. It's a box, which means it's a square. These boxes are squares. And to find the area of a square, it's length times length, right? And this is 1 centimeter, right? This is a 1 centimeter box. By the way, when I say 1 centimeter box, I mean that it's 1 centimeter in length all around. Right, so the area in here would be equal to 1 cm square, right? Because you would just square 1 times 1 is still 1. So you just square 1 cm square. Is everybody following so far? Every box is actually 1 centimeter square area. Guys, I didn't give you guys any break. Yeah, but yeah, each one of these boxes will be a 1 centimeter squared box, right? So when you're counting your boxes, you need to know the area for each box. And to get that, again, if it's a 0.2 centimeter box, then of course you got to multiply the 0.2 by 0.2. So let me show you these boxes, these smaller boxes, which are 0.2 centimeters all around. Now they won't do y'all so bad and I'm pretty sure they won't give you guys a graphic with only these small boxes for you guys to come. That's way too much work. Right? You don't need to do that. So these are the 0.2 centimeter boxes. Again, they're 0.2 centimeter boxes because the length is 0.2 centimeters all around. And you can actually take your ruler and measure these. It should be the same length when you measure it on your ruler. So you can take your ruler and measure the graph paper. You will see that they're 1 centimeter all around and 0.2 centimeter for these small boxes. So for these small boxes, the area would be, again, area for a square is 0.2 times 0.2, right? Length square. And that will, of course, give us point. Right? Right? Okay, might not say anything. All right, so approximately, so we know it's approximately 21 centimeter box. So if you know the area of one box, then what would be the area of 20 boxes? This should be easy maths, primary school maths. If I tell you one box is 1 centimeter squared in area, and you count how many boxes approximately within the figure, you should be able to tell me what the area of the figure is. So 20 boxes, each box is 1 centimeter squared in area. What is the area of the polygon?
20 centimeters.
20 centimeters squared, right? Easy, quick maths, that's how you do it, right? So you just multiply, so the area of the polygon, well, this is not a polygon, this is a figure, right? This doesn't have straight sides all around. So the area for this shape, I just gotta call it, would be equal to our 20 boxes multiplied by the centimeter per each box, which is 1 cm square. So the area would be 20 centimeters square. So to find the area of a polygon, it's find the area of any figure on the graph paper. It's the number of boxes, the total number of boxes, right? Multiplied by the area. Right? Multiplied by the area of a single box. That is it. Right? So take this away and don't forget this. It does show up. I know for it does sometimes show up as a CSEC question. Okay, so I was hoping by now you guys would have realized that 0.2 times 0.2 is not 0.4, it's 0.04. Right? Yeah, let me write this. Should measure now.